Let's get started. Luke, Angela, do you want to get a room? Thank you. I'm sorry. All right. So imagine that you have built a simple serverless architecture in the cloud. So you pick the services really carefully, you connect them all together, and everything just works like magic. And so much so that you decide to go to production with it. And then suddenly hell breaks loose and things start to fail in all possible shapes and forms. And there's nothing you have done wrong, you think, well, except for maybe not reading all the extensive documentation about all the components and all the libraries that you use, but, well, who does that nowadays anyway, right? So what's the next logical step? Maybe you just swear off using the architecture and services in question ever again, well, because they just don't work. And what's wrong with the cloud anyway? And serverless is just an expensive fad, and let's just all go back on-prem and use good old monoliths. Yay! But maybe purely statistically speaking, we should consider that maybe, just maybe, the problem is not the cloud or the cloud provider, maybe not even the services, or even not the architecture. So what is it then? As Murphy's law says, anything that can go wrong will go wrong. Though I personally prefer the extended version of it that says anything that can go wrong will go wrong at the worst possible time. My name is Anahit. I'm lead cloud software engineer at a company called Solita. And I'm also an AWS data hero. And I constantly need to remind that that doesn't mean that AWS tells me what to say and pays me for that. I'm still expressing my own personal thoughts and experiences. And one funny thing I noticed after becoming an AWS hero, people just started to come to me with this smirk on their face asking, so tell us now, what's wrong with the cloud? Why doesn't it just work? So I'm here today to finally answer that question. Well, maybe not exactly that question, but I want us to look together at something that we as humans don't usually feel comfortable looking at. Failures. And to that I say, if something doesn't feel comfortable, let's do it more often. And that I hope that this talk helps you to become a bit more aware and curious and maybe to spot patterns that others don't necessarily see. And also gives you some tools to ask questions and make conscious and critical decisions, take control into your own hands rather than believing in magic. And we'll see some concrete examples of that. And maybe become a little bit paranoid, but in a good way. Because to borrow words of Martin Kleppmann, in distributed systems, suspicion, paranoia, and pessimism pay off. But before we start talking about distributed systems and all the failures, let's get back to our story for just a little while. It actually had a prequel to it. So once upon a time, you were a developer who started developing software that was supposed to run on a single machine, probably somewhere on-prem. And the only things you really cared about were the so-called functional requirements, so that your code does exactly what it's supposed to, and it has as little bugs as humanly possible. That was your definition of reliability. There, of course, could have been some occasional hardware failures, but you didn't really care much about them. All in all, things were pretty deterministic. Things either worked or they didn't. Next thing you know, you find yourself from the cloud, and maybe using virtual machines. And all of a sudden, you find yourself developing software that requires you to think about things like non-functional requirements. So certain levels of availability and scalability. Reliability and resilience get a whole new meaning now. And you still need to make sure that your functional requirements are satisfied and there are as little bugs as humanly possible, but the complexity level just went up. There's so much more to worry about. And failures are slowly becoming somewhat more pronounced, a bit less deterministic. Welcome to the dark side, the distributed systems, where with great power comes great responsibility. But things don't stop there. Next thing, we jump over to the serverless world. And things start to seem really simple and easy again. You just pick services, you just connect them together, and everything works like magic. And the cloud provider takes care of these major utilities for you, things like reliability, scalability, availability, and you don't really see any machines around. Moreover, the word serverless suggests that you don't need to be looking for any machines around, and your life is so easy again. You only care about your code working, and you don't have any worry in your mind at all. Well, except we know that that's not the end of our story. Because anything that can go wrong will go wrong. So what can go wrong exactly? Let's look at serverless and distributed systems in really simplified terms. So distributed system, simply a bunch of machines connected by a network. And it provides you a lot of new and exciting ways to solve problems and to build solutions, but it also provides you new and exciting ways for things to go wrong. Because resources you are using are not limited to one machine anymore. They are spread around, they are distributed across multiple servers, server racks, data centers, maybe even geolocations. And instead of just one machine that can fail, well, now we have plenty. And those failures can happen on any layer. It can be hardware or software failures, things like operating system, hard drive, CPUs, you name it. And also they can happen in most non-deterministic way possible, and independently from each other as well. But the worst thing is that all of those machines talk to each other via a network. And it is known for one thing in particular. Whenever there is communication happening over network, it will eventually fail. And any cloud is essentially built on top of such distributed systems. That's where their superpower comes from. And the cloud providers take care of the most difficult part of managing the underlying distributed infrastructure and giving this higher level of abstraction that you can use. They abstract the low-level complexity away from you. And they give you access to the shared pool of resources that you can use, things like compute and storage, network, and so on. And they do that at truly massive scale that no individual user can achieve. But especially at the large scale, if something has a tiny little bit probability of failing, it will certainly fail. And serverless managed services are a step up in the abstraction ladder. They make the underlying distributed system almost invisible, almost magical. So much so that you might even forget it's there. But by using serverless or fully managed services, we didn't just magically teleport to a different reality. We are still living in the very same massive physical world with the very same underlying infrastructure and with all its built-in complexities. And of course, the higher level of abstraction makes a lot of things easier, just like with the higher level programming languages. But it also comes with a danger. Being seemingly simple to use, it might give you this false sense of security. And it might also make spotting potential failures that much harder, because, well, they are also abstracted away from you. Because the reality is, failures are still there. They are embedded in the distributed system itself, waiting to show up. And as Leslie Lamport said already in 1987, a distributed system is one in which a failure in a computer you didn't even know existed rendered your own computer unusable. We can kind of rephrase it for serverless as well. And with serverless, rather than seeing hardware failures and things like blue screens, we see failures manifest in a different, sometimes less obvious way. Now, let's climb that one last step in our abstraction ladder, and let's focus on building distributed applications on top of serverless and fully managed services. In essence, we are splitting the problem at hand at smaller pieces, and then for each of the pieces, we are picking a service or a resource that we are going to use, and then we connect them all together with things like events and messages and HTTP requests, all of which are using network. And in essence, a distributed application mirrors the underlying distributed system. It allows you to build solutions in a completely different way, just like distributed systems do, but it also comes with great responsibility. And the architecture that you are going to build is susceptible to similar trade-offs. It is going to be complex. Every piece of it might fail at any given moment in most non-deterministic way possible. And whenever communication happens over network, it will eventually fail. And the special case of this kind of distributed architectures are data architectures, where we are dealing with collecting, processing, and storing large volumes of data, which can be any data that you want to store or process. And and deal with. On one hand, this large amount of data or large volumes makes spotting these failures a bit easier because at large scale, if something has a chance of happening, it will. But on the other hand, failures in data applications can be somewhat not as obvious as, let's say, in client-facing applications. And also, most of the times, if the failure happens while processing the incoming data, nobody is going to resend that data to you. Once that data is lost, it's lost forever. So how do we make our applications more resilient in the face of all those possible failures? Well, we are mirroring the underlying distributed architectures, so it's only wise to look at how cloud providers are dealing with failures in distributed architectures. After all, they have quite some experience with that. And of course, there's a lot of complex algorithms and mechanisms at play. But the two of the most essential tools for making distributed applications, distributed systems more resilient are also seemingly simple. They are timeouts and retries. And those are the things that we absolutely need to be aware of when we are building distributed applications. I call them these hidden superpowers, though they are not magical, they are very real. And just like superpowers, they can be extremely powerful, and just like superpowers, they can be used for both good and evil. And we'll see soon what I mean. And you might have noticed that so far I haven't even mentioned any specific cloud provider or any specific service, because this is generic and general for all of them. But now let's finally move on from our fictional story. And kind of time to confess that the fictional story wasn't that fictional after all. In fact, it's something that happened to me, at least to some extent. So I was working with a customer where we're building this simple but powerful distributed architecture for near real-time data streaming at a pretty big scale. So we had a producer application that received the data that we wanted to process. And for that, we took Amazon Kinesis data stream, we connected it to our producer, and on the other end, we connected AWS Lambda to it to consume the data from the stream. And just like that, we built a simple data processing pipeline. And everything was great. Until one day we realized that we were actually losing data. And we didn't even know about it, thanks to the higher level of abstraction. So what was going on there? So first, what is Kinesis Data Streams? Well, it's a fully managed and massively scalable service to stream data on AWS. After you write the data to the stream, you have at least 24 hours to read that data from the stream, to process it, or you can configure it up to a year. And during that time, you can reprocess the data as many times as you want, but you cannot delete the data from the stream. Once it gets to the stream, it stays in the stream for at least 24 hours. And Kinesis is a very powerful tool. It doesn't require you to manage any servers or clusters, and it comes with massive scalability. And to achieve that scalability, Kinesis uses a concept of a shard. And you can think of it as just an ordered queue, and a stream will be composed of multiple such queues. Each shard will come with a limited capacity of 1 megabyte or 1,000 records of incoming data, but the number of shards you can have in the stream is massive. So you can have as many shards as you want to stream as much data as you need. And to stream that data or to write that data to the stream, you essentially have two API calls to choose from. You either write individual records, or then you can batch up to 500 records and send them in a single API request. And batching in general is a more efficient and less resource-intense way of making API calls, and especially in data-intensive applications, there might be a lot of individual API calls if we go that way. So it's a very powerful tool, but again, it comes with some responsibility, and we'll get back to that in just a minute. So we have established by now failures are going to happen in distributed systems and applications, but how do they manifest at this higher level of abstraction with services like Kinesis? Well, it's actually pretty straightforward. Any API call that you make to a service might either fail or it might time out. The good news is that if you are using AWS SDK for making those API calls from your code, SDK will take care of the most of the failures for you. After all, AWS knows firsthand that the failures will happen, so they have built into the SDK this essential tool for better resilience. And once again, with great power comes great responsibility. And this tool is called retries. The potentially bad news now is that we can now turn a localized intermittent problem like network glitches and to a massive one. And if you were at Jimmy's talk earlier, he talked about to some extent. So retries can have unexpected blast radius. They can spread down and cause ripple effect down the line in your architecture and bring the entire system down. So we need to be really mindful of how we implement those retries, how we use them. Luckily, SDK comes with built-in safety measures, and if a request to Kinesis fails, SDK will only handle the request that it can retry, so-called retriable errors, so things like service unavailable or other transient 500 errors or timeouts. And for them, it will retry those failed requests, and it will stop after 3 attempts by default. And it will also use the so-called exponential backoff, where the delay between or time between retry attempts is increasing exponentially. And all of those are small but incredibly important details that can either make it or break it. Because we only want to retry if it can help the situation, so only with transient errors. And also we want to limit the retry attempts and stop retrying if it doesn't improve the situation any longer. So we need the retry limit. We don't want to cause this ripple effect and cause cascading failures in our system. And we want to spread retry attempts as uniformly as humanly possible. We don't want to overload the underlying system. Moreover, SDK gives this superpower to you and allows to configure some of those settings. And the same way it allows you to configure settings related to the second superpower, the timeouts. And if you think that this is not a big deal, well, think again. Because in distributed systems and applications, timeouts are pretty much a given. Let's once again glance under the hood in really simplified terms. So when interacting with a serverless or any other service for that matter, from your code, you are just making an API call, which is abstracted away with SDK method call. And SDK method call will look exactly like a local method invocation. But let's not let that fool us, because we know that the network is still there. It's just abstracted away from us. And whenever there are requests that are made over networks, such as API calls to Kinesis, that request can fail at any given moment. And the worst thing is that we can't even tell if the actual request succeeded or not, because the failure might happen in many different places while you're sending the request. Maybe the processing of the request fails. Maybe it's just waiting in a queue to be processed. Or maybe the response or request went through, but the response never got back to you. We don't know. There are many reasons for that. But the end result is still the same. We are stuck waiting for something that might not ever happen. And this is true for any service, no matter how serverless or not it is. And this is true for Kinesis as well. And so to avoid that waiting forever, AWS SDK has built in this second tool, essential tool for resilience, timeouts. And the ability to configure the timeouts is the superpower that you can use. But once again, you need to be very mindful, because picking the right timeout value is not a simple task at all. Just like any other decision in your architecture, it will come with trade-offs. Too long timeout will probably be inefficient and also might cause some latencies in your application. Too short timeout might start retrying too early, which means you don't give a chance to the original request to go through, and as a result, you might overload the underlying system with all these retry attempts. And ultimately, once again, cause these ripple effects and kill the entire system, have cascading failures. And on top of that, appropriate timeout will be different for every single service that you are going to use. But for all the services, AWS SDK will wait for 2 entire minutes before it retries a request. Just think about it for a second. We are dealing with low latency services like Kinesis or, let's say, DynamoDB. And here we are waiting for 2 minutes, doing absolutely nothing, waiting for a request to timeout. And add on top of that all the possible retry attempts and whatnot, and we may end up in a situation where we are just stuck waiting for something that will never happen. So it's extremely important to configure those timeout values properly. And here we get to the first reason for losing data in our application. Just going with the defaults and waiting for too long can exhaust the resources of your producer application, and it will not be able to accept new incoming requests. And that's exactly what we were observing. And because of likely some temporary issue with the service or the network, we now turned that small issue into a complete system outage, which is the exact opposite from what a resilient system should be. So make the use of these superpowers given to you. Don't just go blindly with the defaults. Defaults can be really dangerous. Right, so far I've been talking about these inevitable failures that are innate to distributed systems in general. But there's another type of failures that are actually caused by the cloud providers themselves on purpose. Those are the so-called throttlings, or hitting the service limits and failing because of that. And this can be especially confusing because, especially with serverless, we are promised scalability. So we kind of start expecting this endless scalability or infinite scalability. And if something seems too good to be true, well, it's probably just that, because no resource is infinite. And service limits are a manifestation of just that. And sooner or later, we need to face the reality. And the reality is, we do not have the entire cloud at our own disposal. We are sharing all the underlying resources with everybody else. And this, of course, comes with the trade-offs. On one hand, we have this huge pool of resources that we can share together. But on the other hand, we might end up in a situation where a single user will try to monopolize those resources. And while resources are not infinite, it will cause degradation of the service for everybody else. So service limits are there to prevent this situation from happening. And throttling is the tool to enforce those service limits. For example, in Kinesis, we had this 1 megabyte or 1,000 records per second for each shard. And if we exceed that limit, new requests will be throttled. They will fail. And this brings me to the next reason for losing data. So I said that SDK handles most of the failures for you, but there's a catch. Because in the case of batch operations, like we have put records here, instead of just handling the failures of the entire request, we should also handle the so-called partial failures. Because batch operations are not atomic. They are not either all succeeds or all fails. Part of your batch might succeed, but the other part might fail, and you will still get a success response back. I'll go one step further. Every single record in your batch can fail, and you still get a success response back. So it's your responsibility to detect those failures and to handle them properly. And the main reason for those failures is exactly reaching service limits or throttling. And when implementing partial failure retries or any retries, we have already seen from what AWS does at the SDK level that there are 3 key things to remember. We only want to retry if it can actually help, so transient errors. We want to set up the upper limit for the retries. We want to stop retrying if it's not efficient anymore or effective anymore. And we want to spread retry attempts as uniformly as possible. We don't want to overwhelm the underlying system with these bursts of retries, because we are probably already dealing with throttling, so we are already reaching the service limits. So let's not overwhelm it even more. And for that, we can use exponential backoff and jitter. And once again, as Jimmy described that earlier, it is a very effective tool, though it's very simple. You just add a simple random component to your exponential backoff, and that helps spread the retry attempts more uniformly. And that's exactly what SDK is using. I just didn't mention it. So if you remember anything at all from this talk, I'd ask you to be partial failures of batch operations and retries with exponential backoffs and jitter. Those things will save you a lot of headache when you are building any distributed application whatsoever. Sorry. And to borrow words of Gregor Hoppe, retries have brought more distributed systems down than all the other causes together. And of course, this doesn't mean that we shouldn't retry, but we should be very mindful about how we do the retries. We don't want to kill the system that's under a lot of stress. Speaking of which, let's see now what happens when we just let the error handling slide and just go with the defaults. After all, that's the easy thing to do, but real life is rarely easy. And it turns out that things can escalate pretty quickly. So remember the other part of our architecture. We had this Lambda function acting as a stream consumer. And Lambda itself is a prime representative for distributed architectures. It consists of many different components that work behind the scenes together to make it so very powerful. And one such important component is called the event source mapping. And when you are touching Lambda to read data from Kinesis stream or some other event resources as well, you are in fact attaching an event source mapping to that resource, and then event source mapping will pick the records from the stream, patch them together, and invoke your Lambda function. And records will be picked from all the shards in the stream in parallel. And you can have up to 10 lambdas reading from each shard in the stream. And here is where the power of concurrent processing kicks in, because we can parallelize reading from the stream now. We can speed things up. But with great power comes great responsibility. And here we can easily reach another important limit called lambda concurrency limit, because nothing is infinite, not even lambda. And with parallelization factor, we might end up having up to 10 times as many concurrent lambdas reading from the stream as we have shards. And lambda concurrency limit just means that we can have a limited amount of concurrent lambdas running in the same account in the same region at the same time. And by default, it's 1,000, though I've heard that new accounts only get 100, which is incredibly low number. And this is a soft limit. You can ask for an increase, but there still is going to be a limit. And once you reach that limit, all the new lambda invocations in that account in that region will be throttled. They will fail. So in case of Kinesis, imagine you have a stream with 100 shards, parallelization factor of 10, and here we are having 1,000 lambdas just reading from the stream. And everything is going to be fine until somebody else deploys another very important lambda in your account, in your region, and that lambda starts to fail, because you don't have lambda concurrency left anymore to use. So it's a limit that can have a really, really big blast radius, and it can cause this ripple effect way beyond your own application, way beyond your own architecture. But let's now go back to reading data from the stream. What happens if that fails? Once again, there is a good news and the bad news. So the good news is that the event source mapping comes with a pretty extensive error handling capabilities. But to use them, you need to know where to look. So the bad news is that the chances are pretty high that you are just blindly going to go with the defaults. And we know that defaults can be dangerous. So what happens when lambda fails? Let's say there was a bad record in a batch that it couldn't process some corrupt data. You just let it slide, and lambda just throws an error that you didn't catch because, well, your code would never fail, right? So although in this case no amount of retries will really help because there is just a bad record, but by default, lambda will be retrying that failed batch of records over and over and over and over again until it either succeeds or until the data in the batch expires. And in case of Kinesis, we know that it's at least 24 hours. So for at least a day, lambda will be retrying that one unfortunate batch of records. And you can imagine the number of unnecessary lambda invocations that we are going to get out of that. Moreover, all those unnecessary invocations will likely cause reprocessing of the same data. Because, you see, from the perspective of the event source mapping, either the entire batch succeeds or the entire batch fails. And even though you might have already successfully processed some records in the batch, whenever a record fails, the entire batch fails, and it causes reprocessing of the entire batch over and over again. So here, records 1, 2, and 3 will end up being reprocessed many, many times. And the bad things don't stop there, because while lambda is busy retrying that one batch of records, no other records are being picked from that shard. So all the other shards go on with their lives, but that one shard is stuck because of just one bad record. So that's why it's often referred to as a poison pill record. So it's also a logical way of working, because if you remember, Kinesis promises a shard-level ordering. And if lambda would just jump over some failed records and continue processing and then maybe reprocess that failures in the background, well, the order will be lost. So it's not a black magic, or it's not a bug or anything, but this doesn't really make the situation much better, does it? So after all that 24 hours of retry, the poison pill finally is discarded. It leaves the system together with the batch that is partially unprocessed. And now finally your lambda can start picking up new records, right? But the problem here is that at that point of time, your shard is probably filled with records that were written around the same time, so they expire around the same time that the already expired one. So you might end up in a situation where records will just keep expiring and being deleted from your stream before you even have a chance for reading them. A bit like with an overflowing sink that you don't have time to drain. So even though we started with just one bad record, we now ended up with losing a lot of valid and valuable data. And this is exactly what we were seeing in our story, of course. Just like with poorly configured timeouts and retries earlier, we made a small intermittent error, bad record, into a full-blown outage. And as a result, we ended up losing data, causing duplicates and delays, consuming resources, and of course incurring extra costs as well, meanwhile leading absolutely nowhere. And all of this because we didn't know better and we just blindly went with the defaults. And here I just need to remember wise words of Gregor once again. But luckily there are plenty of simple ways to be smarter about retries with Lambda. And first and foremost, we need to configure those those error settings with event source mapping. So the most important things that we need to remember, once again, are timeouts and retry limits. And both of those are configurable in the event source mapping, but both of them are set to -1 by default, so no limit. And there's also other very important settings. I'm not going to go through them today, but it's very important to know about them because they can save you a lot of trouble. And you can use them in any combination that you want. But whatever you do, don't go blindly with the defaults. Defaults can be really dangerous. So we have seen firsthand that sometimes we can cause more problems while trying to solve them. And this is especially true if we don't make these conscious and critical decisions about handling failures. And every such decision will come with trade-offs. Things like timeouts and retries can be extremely powerful, but they can also backfire if we just let the matter slide. And instead of making our architecture more resilient, we might end up in an opposite situation. So next time you build a distributed architecture, I encourage you to be brave, to face the messy reality of the real world, to take control into your own hands rather than believing in magic. Because there's no magic, and that's a good thing. And distributed systems and architectures are extremely powerful, but they are hard, they are complex, which doesn't make them inherently good or bad. And cloud and serverless, fully managed services, they take away a lot of that complexity away from us. They abstract it away, but the complexity didn't disappear anywhere. And again, that's not an inherently good or bad thing. And while we don't need to know every single detail about every single service, that's kind of borderline impossible, but there are fundamental things that are inherent to the distributed systems and the cloud in general. So things like service limits, partial failures, timeouts, retries, backoffs. And those are the fundamental things that we absolutely need to understand. Because otherwise we are just moving in the dark with our eyes closed and hoping that everything's going to be fine. And though distributed systems or architectures are hard, they can also teach us a very valuable skill: to embrace the chaos of the real world. Because each failure can make our architecture better. It can make it more resilient. And though despite our best effort, it's really impossible to build something that will never fail, but there's one thing that we can do. We can learn and grow from every single failure. And as Dr. Werner Vogels likes to remind us, everything fails all the time. That's just the reality of things. So either in life in general or with AWS services in particular, I would argue that the best thing that we can do is to stay calm and be prepared when those failures happen. And that's it from me for today. Thank you very much for listening.